Okay, the last presentation, last but not least, Maciej Mościcki from Allegro. He is a senior software engineer there, and he was responsible for introducing various ML-specific solutions like semantic search or neural network re-ranking. And his presentation is about building a vector search engine. So let's start.
1, 2, 3. Can you hear me well? Okay, yeah. So as Tomek said, the title of this presentation will be Building a Vector Search Engine. So let's start with a basic question first. Sorry. Yeah, let's start by answering the question, what is a vector search? Well, vector search is a kind of search. Sorry. Okay, I'll just use the keyboard. Okay, so vector search is a kind of search where both query and documents are vectors. And the search is performed using some similarity metric, such as inner product, cosine, or Euclidean. So what we do is you would take a query, you would compute the similarity to all of the documents, and you would typically return, for example, top k most similar documents to your query. And this kind of search is also called nearest neighbor search. And if the vectors are obtained using some machine learning models, then it can be used for many useful purposes. For example, you could use it to perform image search, where you would have a machine learning model which is used to create vectors, which are also called embeddings, out of the images, and then you could search for most similar images to your image. And whenever you are building a product which involves vector search, at some point you have to pick a vector search engine. And you could use one of the many dedicated databases which are on the market, for example, Vespa, Pinecone, Weaviate, just to name a few. Or you could use one of the databases which have recently introduced vector search capabilities into them. So that would be like MongoDB, Postgres, or Cassandra. So you can safely pick one of these. But you could also use a different approach. You could use a library. So you would take a library and you would have to build your own vector search engine around it. And the best known library for vector search is called FAISS. It was created by Facebook. So think of this choice as sort of, if you're coming from information retrieval background, think of this choice as sort of choosing between Lucene or Solr or Elasticsearch. So FAISS would be Lucene in that comparison, and Solr would be Milvus or your solution, which builds on top of the library. And during this presentation, we will use FAISS mostly as an excuse to introduce various algorithms and topics around vector search, but you could totally use it in production, and I will share some tips for production deployment later on. Okay, few assumptions for this presentation. Let's imagine that we have a data set of 100 images, and we want to build a vector search solution around it. Let's assume that we have a model which produces 128 dimensional embeddings. And during this presentation, I will show you some results of different algorithms. And please bear in mind that they were computed for one of the data sets that we have in Allegro. But depending on your data set, you may get different results for different algorithms. But this presentation should give you an overview of what is possible with those algorithms. Okay, so how can we go about searching in that scenario? So let's assume here that we have our data set. Let's assume that this is our embedding space. And each point here represents an embedding or a document. And when we have a query, which is pictured in green, what we would do is the naive approach would be that we would load all of the embeddings into memory, and we would compute distances to all of the vectors in our database. So we would compare our query to this vector in the red, that one, and at the end, we would compute distances to all of the vectors. And if this does not sound very efficient, then you are right. This kind of search is called exact search. And for the data set of 100 million images, it would take about 30 seconds to complete on a single core. And this is not the time yet that your users want to wait to, for example, scan their wine or something, they are using your product for. And given that the vector has, that each vector has 128 dimensions, we would look at about 48 gigs of RAM to store them all. And in FAISS, when we do a search with data structures, these data structures are called indices. So this type of data structure that is used for exact search, we would call a index which is called flat index. So as I said, this is not the perfect scenario for your application. So we would need to be faster in practice than 30 seconds. And to do that, well, thankfully, in computer science, as many things in computer science, there are trade-offs in the nearest neighbor search domain. So what we can do is we can trade off accuracy for speed and memory consumption of our search engine. And this kind of search where we have this trade-off is called approximate nearest neighbor search, because we will no longer be returning exact results. They would be approximate. And the area of approximate vector search has been studied extensively for decades. So there are many algorithms that we can use. And in fact, the sole purpose of FAISS's existence is to implement these algorithms. So we will use FAISS to use those algorithms. Okay, so let's start with searching faster. And to do that, I would like to introduce two algorithms, or in FAISS we would call them indices. So the first one would be HNSW, and the other would be called IVF. And let's start with HNSW. And the HNSW stands for Hierarchical Navigable Small Words. And I'm sure you have heard of it because it's by far the most popular algorithm out there. In fact, it is used as a backbone for many databases, such as Quadrant, Vespa, Elasticsearch, and so on. And just to give you a brief overview of how it works, it works in such a way that we would build a graph in which the vertices are our embeddings, right? And this graph will be multi-layered, as pictured here. And when we are searching, we will be searching from the top layer. So that would be our entry point there. And what we will do is we will greedily search for vector which is most similar to our query in that top layer. And in the top layer, the distances between embeddings are the largest. So you can imagine that we can pretty quickly, we can go from being far from the query vector to sort of being in the right area. And when we reach the local minimum in the top layer, we would descend into lower layer and we would do the search again. But this time the distance is a little bit closer. So you can kind of think of it as refining our search. And then we would descend into the bottommost layer where there are all of our embeddings, and we would finally reach our vector that is closest to our query vector. Okay, and the question is, why is HNSW so popular? Well, because it has many useful properties. For example, it's super fast and it's super accurate. It's actually state of the art. So this is really what you want. And also the nice property is that the index can be built incrementally. So as your data set expands over time, you can add more vectors to it. The downside of HNSW is that it has a large memory overhead. So we are looking at about 32 to 512 bytes per vector. So in our case, that would be 1.5 the original size of the dataset. So we would go from 48 gigs of RAM to about 720 gigs of RAM. And in FAISS, we would call this index HNSW flat. Okay. The other index that I want to mention is called IVF. And IVF stands for inverted file. And the concept comes from information retrieval. And I would like to explain it in more detail because it's really simple and elegant. So once again, please imagine that this is our embedding space and that we have a query vector queue. So what we would do with IVF is we would divide our embedding space into clusters. And this cluster would be called also Voronoi cells. So you can imagine that the red lines are cluster boundaries. And what we would do is that for each cluster, we will have a artificial vector, which we also call centroid, which will represent this cluster. So they are the blue dots here. And in query time, what we do is we will compute the distance between query and all of these centroids. So here we would compute 3 distances, and we would pick k closest centroids. So in our case, k is equal to 2, but this is configurable number. And we will only perform search in the 2 clusters that these centroids represent. So we would only search in the left cluster and the bottom cluster. So you can see that if the distribution of vectors is even, we will only look, we would only need to compute distances to vectors in k out of n clusters. So that would be k out of n distances for the whole data set. So this number k is the hyperparameter, the knob that we can turn to make the search faster or more accurate. And you may ask, how do we obtain these centroids? How do we obtain those clusters? Well, to do that, we can use a classic machine learning algorithm. It's called k-means. And the process of obtaining these centroids is called training the index. And this example here is also good to show how approximate nearest neighbor search can return results that are not accurate. So let's say that we actually perform the search with IVF here. What we would see is that we would return that the vector, which is green, would be our nearest neighbor to the query vector. And the real answer is that our nearest neighbor was the one in the orange, but we didn't return it because it was in a cluster which we didn't consider. So you can see here that these are the risks associated with approximate nearest neighbor search, because we didn't return exact results. So that is always the risk. So to summarize IVF, it's pretty fast, it's accurate. It's not as fast and not as accurate as HNSW, but it's still pretty good. And the good thing is that it has low memory overhead, so about 8 bytes per vector. The downside is that this algorithm requires training. So as I said, you have to compute those centroids, those clusters. And in FAISS, we would call this type of index IVF n flat, where n is the number of clusters or centroids. And it turns out you don't have to use a single index. You can use compound indices, which merge 2 indices together. So going back to our example, when we did searching IVF, what we had to do for each query is we needed to compute the distance between the query and all of these centroids. And this may not be an issue for like 3 centroids or 1,000 centroids, but if you have very large indices which have hundreds of thousands of centroids, this is a huge constant overhead that you have for each query. But it turns out we don't have to compute distances to all of these centroids, because we can use HNSW, for example, to perform faster search only for the centroids. So we would build a graph of indices only for the centroids, and that would make the first step of IVF, which is computing distances to the centroids, faster, because we would do that approximately. And in FAISS, we would call that index IVF HNSW. What are the strengths of weaknesses of IVF HNSW? Well, it's faster than IVF, obviously, because we are doing the first step of the algorithm approximately. It's still accurate, slightly less accurate than IVF, and it has low memory overhead as well, because the HNSW, which is costly in terms of memory, is only used for these centroids. It's actually a good choice for large data sets. The downside is that it still requires training, well, because it uses IVF underneath. Okay, so now that we know the algorithms that can make our search engine faster, let's go back to our data set and compare some of the algorithms, let's say IVF, to the exact search, which I mentioned in the beginning. And I will demonstrate the differences for this data set, which is 15 million of elements, because it's enough to show the differences. So if we do just that and we perform exact search on the data set of 15 million elements, we will see that its latency is about a second. And if we do the same query with IVF index, which has 65,000 centroids, and k equal to 1, which means that we are visiting one cluster in search time, we will see that the latency is only 4 milliseconds. And this is pretty amazing because that is less than 1% of the original latency. But that may sound suspicious because I have previously said that in order to gain speed, we would need to sacrifice accuracy. So let's now see how we can assess how we can assess accuracy impact. The topic of assessing the impact, the accuracy impact is called index evaluation. So let's say that we are building a approximate nearest neighbor solution. What is our objective? Well, our objective is that we want to return results that are closest to the query. And what is the optimal result, the absolute best that we can achieve? These results are called true nearest neighbors. These are the results from our exact search because exact search is returning the exact results as the name suggests. So this may be counterintuitive, but if we are building a product with vector search, we don't actually care whether the search engine returns results that are of good quality because the machine learning model would need to take care of that. We as the engineers providing the search solution, we only care if we provide the results that are as close to exact search as possible. So that is our goal. And to quantify this resemblance to exact search, we can use a quality metric. It is called recall at k. And the idea is that we will have a query, and we will perform this query against exact index. And it will return some results. For example, these are the vector IDs that the query returned. And we will do the same for the index that we are evaluating. And then we would take top k neighbors from this result set. So in our case, k is equal to 5. So we would take 5 closest neighbors to from the first query and 5 from the second query. And then we would compute intersection of those result sets. So in our case, we have neighbors 1 to 3 in common because they are present in both data sets. And what we would do is then we would calculate the size of that intersection over k, which is, we had 3 neighbors in common, which is 3 over 5, which is equal to 0.6. So if we say something like recall at 5 is equal to 0.6, that will like be the fancy way of saying out of 5 nearest neighbors, 3 were true nearest neighbors. And we would take this approach, you would run many queries, and you would average the recall at k. And this you would have the metric, which will be used to compare indices. So going back to our previous example, when we compared exact search to IVF, to make this comparison fair, we would also need to include accuracy metric, for example, recall at 10. And as I said, exact search provides perfect results. So recall at 10 would be equal to 1. And if you run evaluation for the IVF, you would see that its accuracy is only about 0.5, which is to say that only half of the neighbors that we return for the query were true nearest neighbors. But when we increase the number of centroids, which is the hyperparameter k, we can see that this is the knob I was talking about. We can make the search longer, have it higher latency, but it will provide better recall. So the sweet spot here is around 256 centroids, where the latency is less than 10 milliseconds and the recall is almost perfect. So as you can see, the evaluation is pretty important because like at the end, you will use, for example, A/B tests to assess the quality of your search engine, but you can use evaluation to pick the best candidates for A/B tests. For example, if you would have 2 indices, when the recall is similar, then you would pick the faster index because the quality would be the same. And evaluation can also be used to detect data drifts. For example, I have recently listened to a podcast by Matthias Dose, and he's the author of FAISS. He works at Facebook. And in this podcast, he mentioned that when, for example, the new filter on Instagram appears or a new meme appears on Facebook, the distribution of their vectors changes. So that may be a good point to retrain your index because the metadata associated with your index may drift. So it may not be as performant. Okay, so now that we know how to perform evaluation, now that we know how to make our search faster, we can go back to our original dataset of 100 million images. And for exact search, as I said in the beginning, it would take about 30 seconds to complete, right? And if we pick an index, such as IVF, HNSW, we would see that it has a latency of only 30 milliseconds. And the recall is about 0.85. So we sped up our index from initially 30 seconds to only 30 milliseconds without a huge recall sacrifice. But we only know that because we measured the quality of our index. So the tip that I would give you is to always measure the quality of your indices. Okay, so far we were able to make our vector search faster. The another topic I would like to focus on is vector compression, which is to make our indices smaller, for them to consume less memory. So let's take a look into vector compression algorithms. And the algorithms that are popular in this domain are scalar quantization, product quantization, and some dimensional reduction techniques such as PCA. Okay, so let's start with scalar quantization. So when we have embeddings, they are typically composed of 32-bit floats, right? And the thing is with floats that we normally don't use the Hurl range. So this is the range of IEEE float. As you can see, is pretty wide. And usually the embeddings that are produced by our machine learning models, they tend to have in practice a range more like -8 to 10. So the whole range outside of the actual range is essentially wasted. So we can use that fact to make our vectors smaller. And the idea is that with scalar quantization, we would take the actual range and divide it into buckets. And the number of buckets depends on the number of bits that we want to use. For example, if we want to use 8 bits, we would divide this range into 2 to the power of 8 buckets. And whenever we have float value, we would assign it to one of these buckets, depending on where it lies on the x-axis. And instead of storing the real value, we would be only storing the ID of that bucket. So for example, if the value lands here, we would assign it the ID of 2. And these buckets are also what we call code points. And as you can probably see here, we are using 8 bits, and we initially used 32 bits. So we are decreasing the memory. We have the compression ratio of 4 here. And this is also the knob that we can turn. So we can use 16 bits for that, or you can use something like 6 bits. And in FAISS, this kind of compression will be called SQ, and then the number of bits. Okay, so we have this knob that we can turn. Making the number of bits larger would obviously yield better results, but it would also make index larger. So let's see the results on our dataset. Okay, so previously we had no compression, hence the word flat at the end. And our index was about 48 gigs of RAM. And if we use SQ FP16, we would see that the recall of our search engine is dissimilar, and our size index was sliced in half. So this essentially means that we saved 50% of RAM, and we haven't lost any accuracy. So for many workloads, SQ FP16 would be lossless, basically lossless. And if we go even further and use SQ8, we would see that the size of the index is about the quarter of the original size, so only 13 gigabytes, and recall is very, very similar. So basically no significant accuracy loss, and we are using only 1/4 of the original memory, which is pretty great. But you don't have to stop at the compression rate of 4. You can go even further. For example, you can use product quantization. And the basic idea is that we will split our vector into subvectors. So let's say that we have our 128-dimensional embeddings, and we divide it into 64 subvectors, where each subvector has only 2 dimensions. So as shown in the picture. And what we will do is we will constrain these subvectors to one of the predefined code points. And the number of code points, again, depends on the number of bits that we want to use. So if we want to use 8 bits for each subvector, then each subvector would be constrained to one of the 2 to the power of 8 unique values, which is 256. And how do we obtain these code points? Well, in training, we would run k-means alongside the dimensions of each subvector. So we would run k-means for these 2 dimensions, and we would select the code points that are best approximation of the dimensions of these dimensions, and we would do the same for each of these subvectors. And the total set of vectors that we can represent using this technique is equal to the Cartesian product of all of these code points. So in our case, that's 2 to the power of 8 to the power of 64. And because of the Cartesian product, this technique is called product quantization. And in FAISS, we would call this index PQ64x8, which means we are using 64 subvectors, and each subvector has 8 bits. So previously, we used 32 bits per float, and now we would be using only 8 bits per 2 floats. So that is 8, decompression ratio of 8. And going back to our data set, we would see that the size of our index is only about 7 gigabytes from initial 48 gigabytes, but the recall drop this time is significant. So in cases like this, it may be useful to perform A/B tests to assess the impact on your business metrics. Okay, so what we learned so far is we learned how to make our search faster, we learned how to make it linear, and we learned how to evaluate our indices. So let's see how we can orchestrate building our indices. And to do that, what we would have typically with FAISS is we would have a batch job, for example, scheduled with Airflow, and we would pass our documents, for example, AMR images, through the machine learning model, which would produce embeddings periodically. And then we would take these embeddings and we would train our index. And for some type of indices, for example, IVF, it quickly becomes infeasible to do this on CPU. If you have millions of vectors, K-means is really computationally expensive. So in FAISS, you can use, for example, GPU to produce the index. And then the next stage is you would put your embeddings into the trained index, and you would have index that is populated. And you would run this job periodically, and you would store the populated index in S3 or something other blob storage. Okay, so now we have an index which is populated periodically. How can we deploy it? Well, FAISS is written in C++ and has C API. So this API means that we can use any language that has foreign function interface. For example, if you come from JVM background as me, we could use GNI or Panama to call FAISS. But FAISS also has Python bindings, and the easiest thing to do is actually to embed the index inside Python service. So for hosting our search engine, we could use a simple architecture like this. We would have the machine learning model, which can be used, for example, in Onyx runtime format, and we would have index which was loaded using Python library for FAISS. And good thing about FAISS and Onyx runtime is that both of these libraries are written in C++, and they release Python interpreter log, so Python global interpreter log when they're entered. So this means that you can use regular Python threads, and you can achieve parallelism of your requests. So you can use regular Python server and still get parallelism in your server. So no need to go to Java or something else. Yeah, so what would you do is you would spin up your instance, load the model and the index, and then when the query comes, you would embed the query, you would run it against our index, and you would return document IDs or document ID depending on your use case. But is using FAISS in production a good idea? Well, there are pros and cons. For the pros, you have full control over memory versus recall versus accuracy trade-off. And in some cases, this may be useful. If you use this approach where you embed the model and the index in the same service, then you have all-in-one service that can be easily end-to-end tested. No need for complicated deployments. And if you use Onyx, for example, and FAISS, you can have a simple Python-based deployment. The bad things about FAISS, there is a problem of live ingestion, so it's hard to build index incrementally. And there are poor filtering capabilities. So usually with search, there are requirements that you would like to filter your data. And FAISS can do that efficiently, so there are other search engines that can do that. And as you may imagine, you have to write quite a bit of orchestration code to make it work. But as all things in computer science, the answer would be it depends if you should use it or not. We at Alrego have successfully done it for years. It did well in our scale in many areas, but we are also looking into regular vector databases in the future. Okay, so things that I would like you to remember from this presentation. I would say that vector search is a fascinating domain, and you should not be afraid of trying different algorithms. If you want to stay with HNSW forever, that's fine. But if you want to experiment, FAISS is an excellent library for that. I would also add that please remember to evaluate your indices, because you can catch data drifts or select better candidates for your production or A/B tests. And I would say scale up before you scale out. We have this tendency right now to make everything horizontally scalable, to shard our databases. But vector search has this nice property that vectors can be easily compressed. So consider using vector compression to decrease the memory footprint of your application. It would make your life easier. And you should try something like SQFP16 or SQ8, because it should give amazing results without accuracy loss. Yeah, and last one slide. If you want to work on topics similar to that, we are actually hiring for the software engineer in machine learning role. So our MLOps team, you can Google it or you can reach me after this talk. Yeah, and that would be it. Thank you very much. Here are links to some of my socials. If you want to chat after this presentation, please approach me. Thank you.
Do we have any questions?
Thank you for presentation. In the beginning, you mentioned different distance functions, Euclidean or cosine. Do we have any difference in terms of accuracy and performance among them? Or it doesn't matter which function to choose?
Yeah, I would say that from the literature point of view, as far as I remember, for example, the inner product is better used for applications where the frequency of something in your data set would mean that it should get a higher score. For example, you would prefer popular items, and cosine, for example, would be typically more fair. So it would not consider the items that are more frequent to be better, for example. But in terms of the performance, I'm not sure. I would say that it is not significant in terms of the latency overhead.
Thank you.
Hello, thanks for your presentation. I have maybe a picky or a simple technical question, but I was intrigued by that. When you do the compression of the vectors, if a query point is outside the range of how is it handled?
Yeah. I would say that there are probably many different strategies, but the easiest one is to just clamp it to the, for example, if it's out of the left boundary, then you would pick the leftmost, code point. That would be the simplest solution.
Okay, I have one more question. You said about retraining of indices, and how much time does it take? For example, in your case, that you
for training or
yeah, for training.
Yeah, so I would say, yeah, if you're using GPU, obviously that depends on the GPU that you use. But I would say from my experience, like training the indices of size of about 100 million with IVF, it would take a couple of hours. So between like 5 to maybe 7 hours on Tesla T4 GPU. But the good thing about training is that you don't have to do this every day, because as long as the data distribution doesn't change between days, you can reuse trained indexes from like previous days and so on, because you have so many training points usually with those data sizes that it would not affect the accuracy of your index if, for example, only less than 1% of things changed between days. So you can reuse trained indices.